Okay, so let's look at number 16, where we have the limit as x approaches infinity of 1 plus 1 over x to the x. Now notice as x approaches infinity, 1 over x is going to be getting closer to 0, therefore this base is approaching 1, and the exponent x is approaching infinity. So we've got this quantity, 1 plus 1 over x, it doesn't equal 1, but it's getting closer and closer and closer to 1, and we have the exponent x, which is not infinity, but it's going off toward infinity. And so this is an indeterminate form, but we can't use L'Hopital's rule at this point because of the fact that we don't have 0 over 0 or infinity over infinity. So what we need to do is, like we did in number 15, we're going to let y equal the limit as x approaches infinity of 1 plus 1 over x to the x. Then we're going to take the natural log of both sides. And so we have the fact that the natural log of y is equal to the natural log of the limit as x approaches infinity of 1 plus 1 over x to the x. But recall that what we can do here is we can say that the natural log of the limit is equal to the limit of the natural log of the function. Using our log rules, it's going to happen from time to time. Using our log rules, we have the limit as x approaches infinity of x times the natural log of 1 plus 1 over x. And I'm going to write 1 over x as x to the negative 1. Now, as x goes off to infinity, 1 plus 1 over x is approaching 1. The natural log of 1 is 0, and x is going off to infinity. So we've changed from one indeterminate form, 1 to the infinity, to the next one, which is 0 times infinity. Okay, so we still have that issue that we're going to need to address, but just like what we did previously in some examples, when we have 0 times infinity, a function approaching 0 times a function approaching infinity, what we're going to do is we're going to divide by 1 over x. Multiplying by x is the same as multiplying by 1 over x, and I'm going to not write 1 over x as 1 over x, I'm going to write it as x to the negative 1. Now, as x approaches infinity, you'll notice that what we have is 0 over 0, which is indeterminate, and it is in a form that allows me to invoke L'Hopital's rule. So now, to do L'Hopital's rule, what I'm going to do is I'm going to say, okay, so I've got the limit of the natural log of 1 plus 1 over x. And the derivative of the natural log of u is 1 over u du. Now we also have to divide by the derivative of x to the negative 1, which is negative 1 x to the negative 2. So negative 1 x to the negative 2 divided by negative 1 x to the negative 2 is 1 over 1. So we have the limit as x approaches infinity of 1 over 1 plus 1 over x. We've already said that as x goes off to infinity, 1 over x is approaching 0. And so we're approaching 1 over 1 plus 0, which is 1 over 1, or 1. So we're approaching, if y is approaching the limit as x approaches infinity of 1 plus 1 over x to the x, the natural log of y is approaching 1. Let's come up here. The natural log of y is approaching 1. If the natural log of y is approaching 1, this is e, that's e to the first. So y is approaching e to the first. The limit, therefore, let's write this in a little bit different color. So the limit as x approaches infinity of 1 plus 1 over x to the x is equal to e. We've seen this before in math. That, in fact, is the definition of E. That's something we've not been able to prove before until we've gotten here. Okay, and it's L'Hopital's that allows me to prove that. So a number of times I'll have students in pre-calculus and in calculus say, so how do you prove that that's it? You know, we show it and we say it's approaching E, but here's the proof that the limit as x approaches infinity of 1 plus 1 over x to the x is in fact equal to E. Okay. All right, let's keep going. Other indeterminate forms. What if I have 0 to the 0? How do I handle the form of 0 to the 0? Well, it's going to be the exact same thing. I shouldn't have to spend too much time here. I've got 3 examples. I probably am not going to do all 3, simply because I handle all 3 of them the same way. So for number 17, fighting with my program again, we're going to let y equal the limit as x approaches 0 from the right of the sine of x to the x. To get the function x out of the exponent, we're going to have to use logarithms. That's the whole purpose of logarithms. That's what they accomplish. So I'm going to take the natural log of both sides. And then finding the natural log of the limit of the sine of x over x is the same as finding the limit of the natural log of the sine of x over x. And so that equals, where we go here, the limit as x approaches 0, log rules, tell me that's x times the natural log of the sine of x. Now as x approaches 0, the sine of x is approaching 0, and I've got the natural log of 0. That's an infinity. So I've got 0 times an infinity. So I'm going to have to now divide. I'm going to do the same thing I did before. Let's come up here. The same thing I did last time. Whoops. Let's make that clearer. So I've got the natural log of y is equal to the limit as x approaches 0 of the natural log of the sine of x divided by 1 over x. So now L'Hopital's, the derivative of the natural log of u is 1 over u du. And now we're also going to divide that by the derivative of x to the negative 1, which is negative x to the negative second. Okay, so now as x is approaching 0, we're going to have the cosine of 0 over the sine of 0 times negative 1 over 0. Actually, you know what I should do? Let's undo this, and let's move that x to the negative 2 to the top. So this is the same as the natural log, the limit. This is the limit as x approaches 0 of x squared on top, and then that's cosine over sine, which is actually cotangent, or that's going to be tangent in the denominator. Okay. Now as x approaches 0, that's another indeterminate form because that's approaching 0 over 0, which means I can use L'Hopital's rule again. Okay, so the derivative of negative x squared is negative 2x, and the derivative of tangent is secant squared x. Okay, secant squared is the same as cosine, and so this is the limit as x approaches 0 of negative 2x times a cosine squared x. So I have negative 2 times 0 times the cosine squared of 0. Doesn't matter what the cosine of 0 is. It's 1. Squared is 1, but times 0, that's 0. Now don't forget, that's the natural log of y, which equals 0. So that's e. If the natural log of y is approaching 0, that means that y is approaching e to the 0 or 1. So all of that to say that this limit here is 1. It's a lot of work to get to the 1, but that's the work that it takes. Okay, my video is starting to drag a little long, and so rather than do number 18 and number 19, which are done the same way, I want to get on just quickly to the last type of L'Hopital's that you're going to see here. Let's suppose number 20, and again, all three of these are going to work the same way. Okay, so number 20, I have the indeterminate form of an infinity minus an infinity. Now this one's very easy to simplify, right? Or to deal with. I've got the limit as x approaches 1 from the right. This value is approaching infinity. This value is approaching infinity, and we're subtracting those. Notice that L'Hopital's rule needs to be in the form either of 0 over 0, 1 fraction, or infinity over infinity, 1 fraction. And in this case, we have 2 fractions. So to get the 1 fraction into 2 fractions, we combine the fractions. So we're going to have 1 times x minus 1 minus 1 times the natural log of x divided by x minus 1 times the natural log of x. We simply combine the 2 fractions. Okay, so we're going to have x minus 1 minus the natural log of x divided by x minus 1 natural log of x. Okay. And so, again, if I put 1 in there, I'm going to get 0 over 0. Or actually, I'm going to get infinity minus infinity. That's what I meant to say. I'm going to get infinity and minus infinity. So we're going to do the derivative of the top. 1 is the derivative of x. The derivative of negative 1 is just 0. The derivative of natural log of x is 1 over x. And on the bottom, notice that we have a product rule. So it's the derivative of the first. The derivative of x minus 1 is 1 times the natural log of x plus x minus 1 times the derivative of the natural log of x, which is 1 over x. Okay. So the way that I'm going to handle this next step is, notice I have a denominator of x here and a denominator of x here. I'm simply going to multiply top and bottom both by x. And so we have the limit as x approaches 1 from the right. X minus 1 is my numerator. X times the natural log of x plus x minus 1. Okay. Now if I take the 1 and I substitute it in, I notice that what I'm going to get is I'm going to get 0 over 0, right? If x is 1, 1 minus 1 is 0. 1 times the natural log of 1, well, the natural log of 1 is 0, so this term is 0, plus 1 minus 1, so that's 0. So I have 0 over 0 again. And since I have 0 over 0 again, I'm going to need to invoke L'Hopital's rule again. Okay? Now, truth be told, I got this problem from your textbook, and what's really kind of cool is it says, just do it again, and then this is what you get, because they don't really want to do it either. So the limit as x approaches 1, the derivative of the top is just 1. The derivative of x natural log of x is the derivative of x times the natural log of x plus x times the derivative of the natural log of x plus the derivative of x plus the derivative of negative 1. So I have the limit as x approaches 1 of 1 over, now this is x, times 1 over x, which is 1, plus 1 is 2, plus the natural log of x. If I put 1 in there, the natural log of 1, we all know that that equals 0. And so this just becomes 1/2. And so this limit here is 1/2. L'Hopital's rule. So really, these last couple of problems, what I've done is simply invoked L'Hopital's rule to get, my rules of logarithms or adding fractions. I do my algebraic rules to get it into a form where I can use L'Hopital's rule. Let's do one more just because I know you're having loads of fun. If I'm going to do the limit as x approaches 2 from the right of this minus that, we're going to get a denominator approaching 0, a denominator approaching 0. This is going off to infinity. This is going off to infinity. We have the same thing. We're simply going to combine the two fractions. In this case, we fortunately have the denominator x squared minus 4 and the denominator x squared minus 4, so that we can simply combine my two fractions. I'm going to have 1 minus the square root of x minus 1 divided by x squared minus 4. Now, as x approaches 2, you're going to see that you'll get 0 over 0, so I can use L'Hopital's rule. The derivative on top, the derivative of 1 is 0, the derivative of negative x is negative 1, the derivative of 1 is 0, and down here we have 2x. So notice that as x is approaching 2, right, what are we going to get? We're simply going to get negative 1 over 2 times 2 is negative 1/4. So this limit is a negative 1/4. Okay, the big algebraic skill I needed there was adding fractions, which we all should be able to handle that. Okay, so there you go. L'Hopital's rule. I hope that this is helpful, and you can use that to review as well as to practice.